So in the first lecture, I talked about the invertibility of random matrices with ID entries, and we proved that if A is an n by n matrix with ID entries such that the expectation is 0, the variance of the entries is 1, and for any epsilon greater than 0, the probability that the smallest singular value of A is less than epsilon is bounded by C, epsilon plus e to the negative c, and C capital and C small are absolute constants, and this is universal. We started proving it in the first lecture, completed the proof in the last lecture, and now we can consider another natural class of random matrices. Let's assume that A is a random matrix with entries which are centered of variance 1, but unlike the previous model, let's consider the symmetric model. And one can study the smallest singular value for this model as well. And there was a long-standing conjecture that the same type of inequality is true. And again, if it is true, then it tells us a story. It means that the smallest singular value of a random symmetric matrix behaves like that for a Gaussian or a Wigner matrix until it hits a breakdown, and the breakdown is of Bernoulli type. The probability that two rows of the matrix are the same is, for Bernoulli matrices, is 2 to the negative n, both in symmetric and in non-symmetric case. So this statement, if true, would mean that we also have this only two types of behavior, Gaussian and Bernoulli. This was a long-standing conjecture. It was finally proved last year by Campos, Jensen, Michelin, and Sastrabude. And these are 280 pages papers. I'm not going, of course, go to all details of these papers, but at least I will try to point to some key ideas in their proof. But before it, let's discuss the general approach. The approach will be geometric, but we'll have to adapt it to the symmetric matrices. And this adaptation was the first breakthrough in this problem. The problem attracted attention of many researchers. For example, we did an important work on this problem. But the first breakthrough was by Vershinin, and all the other papers are based on Vershinin's ideas as the first step. And this includes this final this solution of Campos et al. So Vershinin proved a weaker statement, and here I'll assume that the entries are bounded. And then the statement is the following: for the symmetric matrix with ID up to the symmetry entries, the probability that the smallest singular value is less or equal than epsilon is less or equal than epsilon to the power 1/8 plus e to the negative cn to the power c prime for some c prime between 0, 1 and 1, which is an absolute constant. By the way, as usual, the bound on the smallest singular value means also the bound on singularity probability. Just plug in epsilon equals 0. And already from this Vershinian's theorem, you show that the probability of the singularity is super polynomially small. Campos et al. Proved that it is exponentially small. Okay, so how would we approach this? Let's try to recycle our method. And the first big step we made, we reduced this problem to an easier one. We proved that the probability that the smallest singular value of A is less or equal than, sorry, not epsilon, but epsilon over square root of n, of course, is less than epsilon over square root of n, less or equal than the probability that the absolute value of A1 is Q1 is less than epsilon plus e to the negative cn. And here, A1 is the first column of A, and U1 is the unit vector normal orthogonal to the other columns, A2, etc., A, n. This was actually a big step because the minimal singular value is the minimum over X in the sphere of the norm AX. And this step allowed us to get rid of this X, not to consider this minimizing, avoid all discretization steps, etc. Actually, there were some discretization steps in proving this. But as soon as it is done, no traces of X remained here. So this was a big step. Let's try to continue this program. What we said before, in the fully IID case, we noticed that U1 depends on the columns starting from the second to nth. And this means that it is independent of A1. I can condition on these columns. So I condition on U1, consider U1 as a constant vector. And I study this inner product, which is a sum of linear combination of IID random variables. If we try to do it in the symmetric model, we immediately run into a problem. Because let's say that the matrix A is say A1, 1. Here I'll call this vector X. This is going to be X transposed. And this block I will call B. So this is the first column, and this is the block consisting of all other columns. And if I condition on this block, it means that I condition on X as well. So the only degree of freedom I have here is A1, 1, which is obviously not enough in an imagined Bernoulli matrix. So A1, 1 takes only two values. You cannot hope for any exponential or super polynomial probability. So to implement this, we have to be more clever, but we are reluctant to give up on this progress. So let's find this normal vector, and hopefully it will give us an expression which we can handle. So if I write U1 as, say, alpha V, where alpha is real and V is the vector of dimension n minus 1, I can write that U1 is orthogonal to this block as the matrix X, X B. This is an n minus 1 by n matrix times alpha V equals 0. This is just the orthogonality condition, and we add to it a condition that alpha squared plus norm V squared is 1. This is a unit normal. Then we can solve it, and it takes 2 lines to solve it and translate this term into the term depending on X and B. And let me write it down. The absolute value of A1 U1 here is just an elementary linear algebra calculation, is going to be the absolute value of X B X minus A11 over the square root of 1 plus the norm of B X squared square rooted. Okay, now if you follow this this roadmap, we have to take this expression, plug it in here, and try to estimate the probability. Well, here we hit, sorry, not B, B inverse. Here we have many problems. First of all, I wrote here B inverse. A priori, B is not necessarily invertible. But this is a cosmetic problem. Even if I deal with the discrete random variables, I can add an infinitesimally small continuous noise, and I can assume that B is almost surely invertible. Good. But now, how to handle this monster? The dependence on independent random variables here is very convoluted. Instead of the linear form, we get a quadratic form here. And moreover, the coefficients of this quadratic form are random, and the randomness is very complicated. So first, let's simplify the denominator. Without much effort, I can drop this one. Let's see. The reason is that with very high probability, this norm is at least a constant. Let's check it. I can write that the norm of X is the norm of B inverse X. Also equal than the norm of B times the norm of B inverse X. Okay, so the norm of X is a vector with independent coordinates of variance 1. The Euclidean norm of X is with high probability concentrated about square root of n. B is a random matrix with IID symmetric matrix with IID entries, the norm of B is also concentrated about square root of n. I'm not going to show it, but showing it is a 5-minute exercise. So here I have square root of n, here I have square root of n. Conclusion, and this both hold with probability exponentially close to 1. Conclusion that the norm of B inverse X is omega of 1 with high probability, with probability almost 1. That's better. So instead of the denominator, I can at this moment write so approximately X B inverse X minus A 1 1 over the norm of B inverse X. Let's try to simplify the denominator even more. Whatever this B inverse is, I have two families of random variables here. One family is the entries of B, and another the entries of X. And if you look at this matrix, the entries of X are independent of the entries of B. So I can condition on B and study this as a random variable, study the denominator as a random variable depending on X. And then I would conclude that the norm of B inverse X is concentrated about the Hilbert-Schmidt norm of B inverse. The Hilbert-Schmidt norm is the square root of the sum of the squares of the entries. So you write the matrix, this matrix as a vector, and this is the Euclidean norm of the vector. Okay, this already we have done already a lot. We simplified the denominator, and the denominator from this moment depends only on one family of random variables, those which are entries of B. But we have to deal with the numerator, Hilbert-Schmidt. We have to deal with the numerator. And the numerator presents another challenge because this is a quadratic form. So let's conclude. We have bound the probability of that. I'll put this Hilbert-Schmidt norm in the right-hand side. Absolute value of X B inverse X minus A 1 1 less than epsilon norm B inverse Hilbert-Schmidt. Here, the right-hand side is random, of course, and I don't know how this norm behaves. It actually is not concentrated, so I cannot replace it by a constant. but at least I can condition on B inverse and study this as a function of X. Okay. And now our main challenge is to handle this probability for a quadratic form. And we know how to do it for a linear form. So the idea is to try to recycle what we know, transfer the linear form, the quadratic form to the linear one. And there is a trick which allows to do it. This is called decoupling. So let's perform an easy decoupling here. Let's square this. So the probability that X minus A11 less than some T squared. I write it as the probability, as the product of such probabilities. And in the first term, I repeat what I have. In the second term, I write the same with another random variable, say X tilde. So this is the probability that X would be inverse X, etc., less than T, times the probability that X tilde inverse X tilde, etc., less than T. Okay, and then I couple these X and X tilde in a special way. Let J, let's pick a subset J of the set of indices, 1 and minus 1. And let's consider X as the vector, say X. Here X reduced to the coordinates J, and 0 plus X reduced to the coordinates, plus 0 X reduced to the coordinates J, a complement. And for shortness, I'll denote it, the first vector by Xj and the second by Xj complement. Now, I promised a coupling, and I'll write X tilde in the same way. X tilde will be the same Xj plus Xj prime, complement prime, where Xj is the same and Xj complement prime is an independent copy of Xj. Let's try to use this, and let's write this expression under the absolute value. Well, first of all, I can consider it under the single probability, and this is less or equal. This probability is going to be less or equal than the probability that x j plus x b inverse of x j plus j complement minus the inner product of x j plus x j complement prime, inner product b inverse x j minus x j complement prime plus absolute value less than 2t. This is just the triangle inequality. If both differ from a1, y11 by less than t, then the difference is differs from 0 by 2t. And then I honestly multiply it through. If I call this 1 and this 2, then 1 is going to be xj b inverse xj plus xj xj complement b inverse xj complement plus 2 xj b inverse xj complement, and 2 is going to be the same thing only with xj, only in these terms we will have primes for xj complement. Now I honestly subtract one from another, and the first term is gone. So 1 minus 2 is going to be xj complement b inverse xj complement minus xj complement prime b inverse xj complement prime plus 2 xj b inverse, and here I have in one copy xj prime, in another copy, xj complement, in another copy xj prime complement, so I have xj minus xj prime complement. And let's look at this expression. So what depends on what here? We have 3 families of independent random variables. Actually, no, even 4 families. B inverse, so the entries of B, xj, xj complement, and xj prime complement. And one term is special here. Only this very last term depends on xj, which means that if I condition on everything else, I will have this first 2 terms which can be considered as constants. And also I'll have this vector which after conditioning can be considered as a constant. So the random variable here is only xj, and I'm down from a quadratic form to a linear one. I performed this decoupling. Okay, so what how can we write it now after we have done all this? So this is what depends on xj. This is junk, and I'll call this junk by some number b, and so I can estimate this. Only I have to square it before. This square is less or equal than the probability that absolute value of xj b inverse more accurately xj b inverse xj complement minus xj complement prime less than 2 t was epsilon norm b inverse Hilbert Schmidt. Sorry. Oh, thank you. Yes. Thank you very much. I've forgotten about it. Minus b absolute value. What is b here? I have no idea. And to take care of this no idea, I'll put a super over b in R. Yes. Yes. Okay, more precisely, I'm going to condition on everything except xj, but I'm going to condition on a typical realization of B. And we'll see what I mean by typical realization. So it is all conditioned on this. Okay. But conditioned or not, I have no idea what this is. Again, this is something, this is not concentrated. It's a number, but I have no idea what this number is. So I'm proving the inequality with unknown right-hand side. This may be completely vacuous. Suppose that this is huge. Fortunately, we can get rid of it. Yes. For a moment, I fixed this J. When I write, no, this is going to be useful, but this will play at the very end. Actually, I'm going to choose a random J at the very end. But for now, for this moment, we can consider J as fixed. Okay, so this is the inequality we have to prove after all these efforts. Well, and I have some unknown quantity here, but I have also some unknown quantity here involving B inverse. Fortunately, these two kill each other because let's remember, we said that, I already raised it, but we said that the norm of B inverse X, the Euclidean norm, is concentrated about the Hilbert-Schmidt norm. But the same is true for this guy. This is also concentrated and about the same thing. If J complement is large enough. Is about norm of B. There's Hilbert-Schmidt. And this allows me $1,000 question. We are going to pick this cardinality very carefully, and again, I'm going to do it at the end. Actually, it's going to be less than a fraction, but only a little less. It's going to be n to some power exactly. Which power? This is the power which appears in Vershinian's theorem. Yes. But ignore this comment for a moment. We are going to return to it later. Okay, so I figured out that the norm of this guy is exactly what I have here. So despite the fact that I have no control on this quantity, and getting a control of it is at least as hard as proving Vershinian's theorem, I don't need it. I can erase it. And instead, I put the norm of the same vector. In the denominator. Maybe I pay a price of a coefficient. Instead of epsilon, I have some k epsilon. K will be a large number. Great. So what do we see here? After we condition on everything here, this is a fixed vector. This is a vector u. And this is a unit vector. So I have supremum over x over b real of the probability that xj u minus b is less than k epsilon, where u is a fixed vector. This is what we know how to handle. We know from the previous lectures, we actually developed a whole theory for it using the Fourier transform. We know that there is a bad set M of these vectors, and if U is not in the bad set, we have a good control on this. So let's write that this is not equal, but less or equal less or equal, and U is in M, is not in M, plus the sum of the same supremum probability, and U is in M. Okay. If U is not in M, again, conditionally on U, I know that this linear combination behaves like a linear combination with when these random coefficients are normal, which means that this probability for any B is bounded by C K epsilon. And this is what we need. Of course, we pay the price. We have a square here. So at the end, it will be not epsilon, but the square root of epsilon. But this is all right, because in Verschirin's theorem, we have even epsilon to the 1/8. So the only term which remains for us to handle is this. And in this term, I can forget about the first part. I'm going to bound the probability that U is in M. It remains bound the probability that U is in M. What was U? U was this B inverse x J complement minus x J complement prime over the norm of this, the same thing. Is in the bad set M. But remember, we already described this bad set M. We did it yesterday, and this is the set. This the set M consists of small balls around the integer points, more precisely of the projections of these balls to the sphere, because we deal with the unit vectors. So we want to say that this normalized vector doesn't fall into M. It doesn't look very easy because of the B inverse, which is a very convoluted thing. So let's get rid of B inverse. First of all, this condition that this belongs to M that let's call 1 over the norm lambda. So there exists lambda greater than 0 such that lambda B inverse of x J complement minus x J complement prime is in M. And now I would be able to get rid of M. I'm going to put M up to put B in the right-hand side. So we want to prove that this probability that lambda times this is in the image of M is exponentially small or super polynomially small. First of all, I'm going to condition on these vectors. So I'm going to regard all this as some fixed vector y. And I don't care which y I get. I'll get a uniform bound for all y in Rn and for all lambda positive. So we fix lambda, we fix y, and we want to prove that the probability of this is small. And here the description of M comes to our help. So M consists of, is a collection of small balls around the integer points. To prove that the image of M doesn't contain a fixed vector lambda y, it's enough to prove that each ball doesn't contain this fixed vector with high probability, and then take the union bound over the balls. So we are down to a single ball. How to handle a single ball? Let's assume that the center of this ball is Z, and then we have to show that for each center Z in M, by the center, I mean the centers of these balls, actually the radial projections to the sphere. The probability that that bz minus lambda y less or equal than some delta square root of n is small. I'm not going to write explicitly what delta is. It's going to be clear from these calculations. But this is our task. If we do this for the center of the ball, it means that with overwhelming probability, this distance is large. And the other points of this ball are close to Z. So for all other points, the distance will be still large. So this is the only thing we have to do. And if we, so Z is a fixed vector, this is a fixed vector, this is a fixed number, nothing is random here. The only randomness is in the matrix P. We want to prove this small ball probability. Well, and we know how to do it if the entries of B are completely independent. This is a standard exercise. But they are not. B is this block, and it is also a symmetric matrix. So we are back to the same challenge. We started with symmetric matrices, and after all this story, we got back to the symmetric matrices. This seems to be unavoidable. So we'll have to do it by brute force. Instead of considering this B, I'm going to consider only a part of it, which has independent entries. Let me write this B in the following way. So this is a symmetric matrix. I'll cut this block, a rectangular block under the diagonal. And the entries of this matrix B prime are going to be IID, fully IID, without any symmetry restriction. And if I condition on all the rest, I can use these entries to get the small ball probability. What do I lose here? I am going to, if B was fully independent, this probability will be less or equal than what I have here, C delta to the power n. And when I do it only using B prime, it's going to be C delta to the power the number of columns of B prime, which is less. So if B prime is, let me call this K, is n minus K by K matrix, I'm going to get here n minus K instead of n. Is it bad or not? Let's see. We have to take the union bound over all these balls. These balls are in Rn, which means that we need a power n. We cannot lose much. And so this K should be much smaller than n. Ideally, it should be 1, but if it is 1, we have one column. This is not enough randomness. We need the rows of B to be somewhat fat to get a good small ball probability. So this is the opposite restriction, that K should be large enough. So these are two competing restrictions, and of course, what is done in practice, you perform all these calculations and optimize over K. And the optimization gives you that K should be n to the power C prime. C prime is less than 1. Well, and this C prime is what you are going to pay here instead of C. And now I can go back to what this J is. Actually, the choice of J is prepared to fit this choice of B prime. The cardinality of J is going to be K, and this J should be random. And then we get, after we do this with the submatrix B prime, we get Vershidin's theorem. I probably don't have time left, but before I finish, let me say a couple of words where we missed the target, where we lost this 1/8 and where we lost this n to the C prime. N to the C prime has a single source. This is cutting out an independent, fully independent block out of the symmetric matrix. If we learn how to use the whole symmetric matrix, we don't need to do it. With the 1/8, it's harder. We have several sources. The first source is the decoupling. We squared. But there is another source which I swept under the rug. I said that the norm of B inverse X is approximately this matrix is not concentrated. And this approximation is not precisely true. If you want to prove it with high probability, this is going to be less or equal than epsilon to the negative 1/2, greater or equal than epsilon to the 1/2. With probability greater or equal than 1 minus epsilon. This we can afford to lose. And these 1/2 contribute to the 1/8. But besides that, not besides that, but nevertheless, we have a whole proof of this bound, this Varshinian's theorem, but with losses. So next time, I'm going to talk about how to get rid of these losses. Thank you.